Assalamualaikum. Hi everyone. We continue with our topic 2 of our multiphase reactor. In this topic, the subtopics will be include multiphase reactor. What are the types of multiphase reactors? The mass balance. We'll be looking at how to calculate the mass balance in multiphase reactors. We'll be looking at the flow configuration, and there will be some kind of example reaction in one phase only, and you'll be introduced to what is interfacial surface area, and there will be calculation on the mass transfer between phases. What is the multiphase reactor equation, equilibrium between phases, gas liquid. We'll be looking at the reaction of gas liquid in multiphase reactors and also the example. So in multiphase reactors, mass transfer usually happens with reaction steps, and mass transfer usually control the overall rate of chemical reactions in multiphase reactor, usually, especially in big reactors. Okay, mass balance and energy balance must be written and solved for each species in each phase, and gravity is one of the important parameter that control the patterns in which the lighter phase will rise and denser phase will fall. And the multiphase reactors, the multiphase, different phases actually promote mixing within phases and also between phases, and this mixing is actually has a dominant effect. And the solubility and phase distributions of species between phases needs a very careful application principles. So the type of multiphase reactors, there are gas liquid and liquid reactors, or gas liquid or gas solid and liquid solid reactors, or three phases, means that there'll be three gas, solid and liquid reactors. So why do we need to use multiphase reactors? Because especially solids process require reacting with gases or liquids. Solids means usually it's the catalyst. And in multiple phase, it requires solid to attain conversions higher, and the equilibrium constraints in a single phase process and can help to improve mixing within in the reactor by allow gravity to cause flows of phases relatively to each other. So if you look at the degree of difficulty with respect to reaction type, the gas liquid without catalyst, it is quite straightforward in terms on how to design, but it's getting more difficult and getting more complex when it goes towards these reactor types in which gas liquid with soluble catalyst is more difficult than gas liquid without catalyst. And then gas liquid with solid catalyst. What's the difference of solid catalyst and soluble catalyst? So soluble catalyst means the catalyst may be in liquid form. So the gas liquid with solid catalyst is more difficult than soluble, The gas liquid with soluble catalyst is more difficult with this one because of this phases occurs. And gas liquid with solid phase with solid catalyst is even the complexest of all. So these are the type of multi-phase reactor. Example of gas liquid and liquid reactors. It could be a spray tower, bubble column, sparger, oil burner, emulsion reactor, membrane reactor, catalytic distillation column. For gas solid and liquid solid, it's slurry reactor, packed bed, moving bed, fluidized bed, riser, circulating fixed bed. CVD is chemical vapor deposition reactor, spin coater, fibers, spinner, crystallizer, conveyor, ore refiner. Okay, you can just read all of this and you can just get the more information on Google or YouTube. And these are the example of three-phase, which are multi-phase solid, trickle bed, gas liquid slurry with solid flow, and also membrane reactor. Alright, this is just to illustrate that the different phases of gas, and there must be also liquid and another type of liquid. Okay, it could be you know, some kind of water, but this one is some kind of more bipolar liquid, and this is together with solid. So at every area here, it shows you some examples of reactor, so you can read it on your own. So another example of multi-phase reactor, we have bubble column here. So you can see this is gas going in and liquid going out, and this gas going through the solid phase of liquid and it goes out. So the same thing as this one, liquid is going inside, going through the catalyst, and it's going out. Okay, this one is maybe just tube reactor. This is the mechanically agitated tank, pack column, tray column, spray column, okay, venturi ejector, motionless mixer. So of all these reactors in this CHE505, we will design a bubble column, a spray column, pack column. The other one is the falling film reactor. Okay, this is example of bubble column, typical bubble column, whereby you have this sparger to disperse air inside the liquid, and the air would usually this is the outlet for the air going out, and the liquids going in and the liquids going out. Okay, so this is so the reaction happens between liquid and also gas. So another example of that taking the concept of bubble column is the trickle bed reactor, or the other name is co-current flow, in which that the gas and liquid has the same direction and it's going out, and they have solid catalyst inside here. And for the slurry reactor, more on the liquid and the bubble. So you can see here the formation is like slurring the liquid between the bubbles and also the catalyst. So, and then another trickle bed reactor, which is the counter current configuration flow, whereby the liquid and the gas is not at the same direction. Okay, this is gas going out, and that is the liquid going in. And both gas and liquid is passing through the solid catalyst. And packed bubble flow reactor. Okay, all these four using the same concept as bubble column reactor. Here, another example of bubble column, multiphase reactor. The bubble column, mechanically agitated tank, the packed column, and this one is the trickle bed, whether it's in co-current flow or counter current flow, and the three-phase fluidized bed, meaning that the gas going inside here, it will make the solid inside here to be fluidized, so mean it's so-called promoting the mixing. So the coalition between liquid and gas and solid would be more, and the reaction, maybe the contact between these spaces would be higher, and the reaction happens also high. So we continue on this next slide.